look at the difference between permutations and combinations and using factorials. So when we talk about permutations, we're worrying about the order. So order matters. Combinations, the order doesn't matter. So if we're choosing 3 letters from 4 available ones, and if the order matters, that means on the first choice, we've got 4 options. Once we've chosen one there, we'll only have 3 letters left. So then we'll put a 3 in the next box and then a 2 in the next box because you have 2 letters left. So that would be 4 times 3 times 2, and that would give us 24. The other way that we can write that is 4 factorial. So if we grab our calculator, we can also do that on our calculator as well. So if we press the math button and we go across to probability, you'll see number 2 is an NPR, so that's the permutation. So we can tell it 4 letters and 3 spaces there, 3 places to put it. The other option is to use the factorial, so we can do the 4 factorial. So we press our 4 first, then math, and then we can arrow down and put that exclamation mark, which is what we use for factorial, and that will give us our 24 as well. Now, so that's when the order matters. So if we had the letters A, B, C or B, A, C, they're different combinations. If the order doesn't matter, we would say that they were the same 2 combinations, so that we would just be getting our choices, whether we're using A, B, C would be one choice, B, C, D. So if we're looking at the letters A, B, C, and D, we could choose A, B, and C, so that would be one choice. We could choose B, C, D, which would be a second choice. If we had C, D, A, that would be a third choice. And then if we had A, B, D would be the 4th choice in any in any order there, because the order doesn't matter. So that's how we get our 4 choices in a working through logical way. The other way we can see that is we use our C here instead of the P, so our combinations rather than permutations. So now we're not worried about order that they're in. If we get A, B, C, that's the same as C, B, A. Whereas up here, they would have been 2 different answers. So we can put that in our calculator using the C this time for our combinations. So if we go math and then across to probability, down here to the NCR, we can then put in the 4, 3, and you'll see we get the answer 4. The other way we can work it out is using our factorial rule, which is that on the top for that 4C3, we would have 4 factorial on the top, and then on the bottom, we would have the 4 take away 3 factorial times 3 factorial, or n minus r factorial and r factorial as our rule there. And when we sub that in, that's how we would get our 4. So the other thing to do with our combination, so when we're using our C, we can use our Pascal's triangle and get those combinations. So if we've got 0 trials, we've got that one way of getting that. When we have 1 trial, we can either have success or failure. So Pascal's triangle is most often used with probability experiments or binomial expansion, where we have 2 options, success or failure. So out of a number of trials, how many successes or failure there are. And that's often how we will use that, or the most way that we use it in maths methods. So looking at a couple of examples of how we can use that, we've got evaluating 5r if r is equal to 0, 1, 2, 3, 4, 5. So a couple of options. We could use Pascal's triangle, and this 5 here tells us we are looking at row 5, and then that would give us our answers of 1, 5, 10, 10, 5, 1 there. The other option is we could go through each individual one and put them into our NCR there and make it, so if we had our 5, 0, and then we would do our 5, 1, and work them all out individually on a calculator, or you could go and work them out all individually using factorials. I find Pascal's triangle the quickest if I'm trying to find a lot of numbers like that. If we're told no calculator, obviously our Pascal's triangle or factorial is the way to go. Now, for 7, 1, I look at the pattern in the triangle and notice that that 0 line is always a 1. The next line is always, so this diagonal here, is where we have our r equals 1. And it's symmetrical, so you'll notice that if you have n minus 1, it's going to be that one there. So whatever that number, like whatever our row number is, that's what our value will be for the 1. So we know that's going to be 7. If we worked that out using our rule that we had, we would have our n factorial on the top, and on the bottom we would have our n minus r factorial timesing by r factorial. So on the top we would have 7 factorial. On the bottom we would have 7 take away 1, which is 6 factorial. And then we would be multiplying that by 1 factorial. So then on the top, we would be doing 7 times 6 times 5 times 4 times 3 times 2 times 1. On the bottom, we would have just 6 factorial. So 6 times 5 times 4 times 3, so that we can cancel it out and say that that would be equal to 7. Or we can write it all out and show that. Then when we've got the 6, 5, like I said before, it's going to be that, instead of being the 6, 1 in. So that one's going to be equal to 6 there. And then the 12, 10, we can use our method that we were doing up in this first one the long way. So we would have 12 factorial, and then we would have 12 take away 10 being multiplied by 10 factorial there. So we've got 12 factorial on the top, and then we've got 2 factorial times 10 factorial on the bottom. And so then we can try and cancel that out. So we know that we would have 12 times 11, and then we would times by 10 factorial on the top. So rather than writing 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, we can write the 10 factorial, and on the bottom that we've got the 2 factorial, 10 factorial, so we can obviously cancel them out. And then that means we know our 2 factorial is just going to be 2 because it's 2 times 1, and then we can do our 12 times 11 on the top, which is 132. So when we divide that by 2, we're going to get 66 there. So that's how we can simplify that one. We can then go into ones where we've got an n there, so an n2, and we're trying to work that out. So using that same rule, we would have our n factorial on the top, and then on the bottom we would have n take 2 factorial times 2 factorial. Now using that process like we did on that previous question where we had the 12, and we knew that was 12 times 11, we know we would have n, and then we would be multiplying by n minus 1. Then we would multiply by n minus 2 and keep going that way, or write n minus 2 factorial. And then on the bottom we've got that n minus 2 factorial times 2 factorial, which is the same as 2. So we're able to cancel out that n minus 2 factorial and leave us just with n outside of n minus 1 over 2, and that means we can simplify it much more easily. We can then go on to ones like this where we then have what that is equal to. So we've already done the first part of that, so we can say n outside of n minus 1 over 2 is equal to 45. So we can multiply by 2, get 90, so n minus 1. Expand that out and we get n squared minus n, and then bring that 90 over, equals 0. And then we can solve that by factorizing. So looking for two things that multiply to give negative 90 but add to give negative 1, we would then have n minus 10 and n plus 9. So then n would be equal to 10 or negative 9, but we can't have a negative, so it would have to be the 10. And then lastly, we can have the type where it's given to us in words, where we've got consider a group of 7 students. How many ways can a group of 3 students be selected? Assuming that order doesn't matter. In that, obviously would then determine which way we go. So if we were doing order did matter, then we would have our 7P3. If we were looking at where order doesn't matter, then we would have 7C3. So we would get 2 different answers depending what the clarification was about whether order mattered or not. So if we were just doing our 7P3, we would have 7, 3, and the answer would be 210 combinations there. If order didn't matter, then we would have our 7C3, and we would get the 35. So always be careful to check if they're saying order matters or doesn't matter.